This talk is about stage relational interpreters running backwards faster, and it brings idea from multi-stage programming, from relational programming, and from how to construct interpreters in those settings. So relational programming is a pure form of logic programming that makes no distinctions between inputs and outputs. And it enables running backwards, meaning you give it the output and it gives you the inputs pretty uniformly. And multi-stage programming is a way to write programs that write programs. And that is useful because you can write a high-level program and generate a low-level program that is specialized to some of the inputs. So the work I'm presenting today is joint work with William Bird, Michael Ballantyne, and Laura Zarmukametova. And it comes from a history of 2 papers, at least. The first one is a unified approach to solving 7 programming problems, which was a functional paper at ICFP 2017. And this paper shows all the things you can do with a relational interpreter. And the second paper is Collapsing Towers of Interpreters in Popple 2018. And this paper shows how you can collapse levels of interpretation without overhead, even in a tower, even in a potentially infinite tower of such levels. And today we will put these ideas together into something new, stage relational interpreters. And so as we've seen, staged means multi-stage programming, and you can do it functionally. And here we've adapted it to the relational setting. And relational means mini-Canren, which is the language we will use, an extension of that language, and turning functions into relations. And interpreters are just evaluators for our purposes. And because we will stage them, they will become compilers. And then running backwards means no distinction between input and output, and faster means without interpretive overhead. So we'll look at these things in more detail. Okay, so now I will do an introduction to mini-Canren, which is a relational programming language embedded in Scheme. And the first thing to think of is the interface to Scheme. So there's this run interface where I take a logic variable and I can say, I want the logic variable to unify with 1. So I get a list of 1 as a result here. And I can also say unify 1 with 2. And then I get the empty list because 1 doesn't unify with 2. So this whole query fails. And I can also say 1 unifies with 1, and then I get that the logic variable is this _.0, which is an unbound logic variable, meaning for any value of it, the query succeeds. Okay, so we've seen unification and we've seen the run interface. Now another thing we can do is conditional. So we can say that either 1 unifies with Q or 2 unifies with Q. And then we get a list with 2 results, 1 and 2. Okay, so we have everything. We don't have quite everything we need. The last thing we need is fresh. So fresh introduces new logic variables and puts them in and what follows is a conjunction of statements. So here I can have so here I get the list of list 1 and logic variables, or I could also say x equals y, and I get this list, or I could also say remove this statement and I get two distinct logic variables. Okay, and finally, what we can do with all this is we can build up relations. So for example, I build up the appendo relation, which takes x, yx, and zs, and says, condy, if x is empty, then ys equals zs. Otherwise, so here I have defined the append function relationally. Let's see if it works. Sorry, this should be ZD. So what we're saying here is that if XS is the empty list, then YS is equal to ZS, where ZS is usually the output, but here is just another argument. And then otherwise, XS is a pair, and the result is also a pair with the same head. And then we recursively find the rest of the result. So let's try this. And we get the right thing. And then we can also try running backwards. So we get the right thing, and we can also try getting and we get all the possible ways of splitting A, B, C, D, E into two lists that append to each other. And just for completeness, I should mention that we also have a run number instead of a run star. So this just returns two results, for example. Okay, so this is what we've seen. So we've seen run star and unification. We've seen condy to do conditionals. We've seen fresh to introduce fresh variables. And we've seen how to define recursive relations. And yeah, so that's it for a crash course on minicannon. There's so much more to it, but that will do for now. So let's get back to minicannon actually and look at Evalo, which is an interpreter written in minicannon for a subset of scheme. And so the object language is scheme and the meta language is minicannon. And we can try it out on some examples. So let's do that. So run one, Q. And that gives us a list of one because the number is self-evaluating. And we can also do a run star instead to see that there's no other answers. Let's do something more interesting. So let's do that also returns one. So now we can actually use Evalo to ask an interesting question, which is what is a program that evaluates to itself? So if I do evaluate QQ. Then I get a number. That's what it means. There's a constraint that the result is a number. Now, if I ask for 2 answers instead, I get a number or I get the value through. So let me ask for 4 answers instead. And here I get an interesting answer, which is that this term is self-evaluating. So let's try it. Let's first rename to X for readability. So that's a quine. And we can try it by just running it in Scheme. And we get the same thing exactly. Okay, so our evaluator is able to generate quine, and that's the true power of relational programming. Now let's use it to turn a function into a relation. So earlier we saw the function appendo defined this way. Now we're going to just write the function append in Scheme, and then see if it can do the same thing. So in Scheme, we could write letrec append Okay, so we get the right thing. And now I can put this in evaluate. And I get the same result. And I can now run it backwards. Let's try this. So I can say, and I indeed get the same result as appendo. So by using this evaluator, this relational evaluator, I'm able to turn a relation like append into, sorry, a function like append into a relation like appendo. Okay. And now for our edification, let's look at the implementation of evaluate, which is really defined like another relation, like appendo is. So evaluate delegates to eval_expo, which also takes an environment. And let's look at the number. Okay, so if the expression is a number, then the resulting val is also that expression. So numbers are self-evaluating. If we have a symbol, we look it up in the environment. If we have a quoted expression, then here we're playing a shortcut where we're saying the result is whatever is quoted. And we have some side conditions to ensure that that quote is not shadowed and that internal interpreter structures are not reflected in the quotation, because otherwise Minikanman plays tricks and sort of quote closures instead of generating lambdas. Okay, and so we have more examples here in the interpreter, but we basically have one case, some cases per form. So for example, this is the case for if we have a one argument function, a variadic argument function, sorry, and here is multiple argument functions. So let's look at either one of them because they're quite similar. So let's look at the multi-argument function. So you have the rater and the rents that match the expression, and the rater should evaluate to a closure, and the rents should evaluate list by list to some values, and then we just extend the environment with those values and evaluate the body from the closure. So you can see that it's sort of a relational way to write a functional interpreter, and that's what it is about. So now we will look at staging in a functional setting, and this setting is that of Pink, one of the languages in collapsing towers of interpreters. And Pink is a polymorphic stage system, and here we're looking at the base VM evaluator, which takes a language that looks like this. So it's fairly low level. So a lambda introduces two bindings, and the first binding is for the recursive call, and the second binding is for the argument to the lambda. And so here, if also succeeds if the condition is not zero. So here we have the factorial function defined as if n is not zero, then we do the recursion here, and n times factorial of n minus 1. Otherwise, we return 1. And we do this, we apply this to 4, so we get 24. Let's try it out. Indeed, we get 24. And then there are various predicates defined. So for example, number 1 returns 1, which, well, 1 here represents the numeric, the Boolean true. So if I did number 2, I would also get 1. And then here we have equality. So we can check whether the plus procedure is equal to car counts of +2, which it should be. And indeed we get 1. And then now we can start generating code. So the way code works is that if the arguments to an elimination form such as plus or if are code, then the whole thing becomes code as well. So here we've lifted the primitives, the primitive numbers, and left everything else abstract. And then here we see that the result is an anormal form. So first we have the if, which contains a let inside, which is which here basically does the plus operation and then returns it as a variable from the let. And then here we have 0 again, because we're lifting this 0. And then the result is a var 0 for the entire if expression. So we have these lets that are nested and so forth. And we can also lift the factorial program. So here we're lifting the introduction, so the 1, and we're lifting the whole lambda as well. And then everything else propagates so that we get the code for the base factorial function, which looks like this indeed. So this is how we stage code. We use this lifting operation, and we rely on elimination form to propagate the lifting. And just as another example, if we do logging, we don't know whether we want to log during the first stage or the second stage. And here the first argument to log is just used to decide whether we're logging now or whether we're generating code that logs. And that's it for a quick introduction to the base evaluator the base evaluator in Pink. And now let's take a look at eval-MS, the stage polymorphic basic evaluator that we just saw. So we have numbers that are self-evaluating. Curiously, symbols are also self-evaluating because actually for variables, we have a special tagged case. This is when we look up the variable in the environment. And so a lambda returns a closure, and then a let sort of does the evaluation of a let. And what's interesting is that a lifting calls this lift procedure, which we'll see in an instant. And furthermore, let's take a look at one of the primitive forms. So for example, plus calls this binary operation, which we'll see in an instant. So let's look at this first, binary operation. So we evaluate the two arguments. And then if they're both code, then we reflect the result as code. We reflect the plus as code. Otherwise, we can actually do the evaluation of the binary operation at this stage. And if they're both, if they diverge in saying what is code, what is not code, then it's an error. We could have been more lenient here and proposed that if one of the arguments is code, then the other is automatically lifted to code, but we wanted to be very clear with our stages in pink, so we didn't do that. And then lift itself is interesting. So lift implements a normalization by evaluation style reify operator from semantics to syntax. So for example, it transforms a closure back into a lambda, and it transforms a pair back into a cons. Okay, so that's all I wanted to say about the base evaluator, the stage polymorphic base evaluator. Okay, so now we will see how to turn an interpreter into a compiler using staging, the general process of it. So as we've seen, staging is a process that produces code, and an interpreter is something that takes code as input, an additional input, and produces a result. So for example, the code could be a regular expression, the input could be a string, and the interpreter could be a matcher that decides whether the input string matches the code regular expression, and we get a result. Now, if we put these two things together, we get a staged interpreter. And what happens is that in the first stage, we leave the additional input symbolic. And in the second stage, we get the actual input to execute from the second stage code. So we have some code as input. With the stage interpreter, we produce code, and ideally this code would be more low level or more condensed. And we produce this code with respect to a symbolic input. And in the second stage, we give the actual input to execute the code to get a result. So if we look at our regular expression example, we again have the input code is a regular expression. Now the additional input, symbolic input, is a code of string as opposed to a string. It's input that represents code in the generated code, but it's not known at this stage. And then we generate low-level code that does some matching for a regular expression. So for example, it matches the first character A. And then we actually run this code with actual input to get a result like true. Okay, so in summary, this is how we turn an interpreter into a compiler. We stage it and we leave the input, the additional input to the interpreter symbolic, while we leave the code static, known at staging time. And then we produce second code that is specialized to the blue code, and with actual input we get the result. So notice the difference is that here, when we look at this example, we're generating code that is specialized to the regular expression. And it's not as high level as the regular expression matcher, which would be an interpreter that goes through the string. So we get rid of the interpretive overhead of parsing the regular expression all the time. Okay. Okay, now let's look at some interpreter Stern compilers. We start with the stage polymorphic metacircular evaluator for pink. And here we have the evaluator takes the evaluator as input, the lifting constructs an expression and an env. And for example, numbers are self-evaluating, but we might lift them depending on the lifting constructs. And a plus is like the base evaluator. A plus inherits whatever the arguments do. So if the arguments generate code, then it will generate code. If the arguments are bare values, then it will apply the plus right there. So anyway, so this is the pink evaluator, and we can see how it works with examples. So for example, here we're evaluating factorial and we get 24. We're evaluating it through through the pink evaluator. So let's just load this. And we can see that factorial looks like this. So now it's higher level than the previous representation in the base evaluator. And now we can evaluate this and get 24. And we can also compile this instead by using the compiler instead of the interpreter. And then we get the A normal form in the low level base evaluator in the low level base language for factorial. So the difference between those two is whether lifting happens or not, depending on the argument that we give to the pink stage polymorphic evaluator. Another thing we can do is log. So we can decide to do something different for variable. If the variable is equal to n, we can decide to log, and that does the right thing and logs the value of n. And then we can also do it in a compiled fashion to generate code with logs. So somehow the modification that happens to the interpreter gets transmitted to the generated code. So this is the example, and we see that we generate code with logs. Okay. And now in pink, we can reproduce the matcher, the regular expression matcher example. And here we have the maybe lift to indicate that maybe we will be a compiler or not. Maybe we'll stage the matcher or not. And so we can see that we handle stars matching here, and the match does both. The match matches here, but starting anywhere. And so how does this work? Well, so we have the maybe lift set to no lifting, and then we evaluate use the pink evaluator, and we get yes. And we have also another example here, and so forth. And then here we can do compilation by setting the lifting here. And now we generate code that when evaluated gives us the results. So that's just to show that a staged interpreter is a compiler. And this is a naive compiler for regular expression matcher, but we can imagine a more sophisticated compiler too if we add optimizations to the staging process. Now let's look at the basic staging constructs in miniCanren. So first recall that unification works as follows. So here we have a query variable Q, and we unify Q with 1, so we get 1 as the output, list of 1 as the output. And now I can do the same, but instead of unifying, I do a lifted unification, meaning you generate code that unifies. So now I get an unbound logic variable, and in the second stage, I can bound this logic variable. I can unify this logic variable to 1. Now this is the same as writing so we have an explicit lifter that takes a goal and lifts it to the second stage. Now let's see what we can do with this. So it's by design fairly limited. It's not very smart. So for example, if you unify list of 1 with list of Q, it's not going to simplify. It's going to make you unify some concepts even though they're not necessary. Like we could have written this instead of this, we could have written just could have written that instead. Okay, so what else can we do? Well, also we can unify a failed unification, but since we're lifting it, we get it in the second stage, then it will fail. And finally, we can maybe do something a little more interesting by unifying and here we get what we expect. Okay, so this was just a quick tour of the staging construct. It's fairly simple. Conceptually, we can add lift to unify, to lift a unification or any other goal that we have. Now, the next step is to stage the interpreter, and this is encapsulated in this gen method. And now we give it a functional program as we did before. We defined append on these arguments with this body. And now, if I just evaluate the gen, I see that I get code as output that does the relational version of append with a little bit of overhead in terms of unifications, but not so much without interpreted overhead. So that's pretty interesting. And let's see whether it behaves like appendo. So it's a regular relation, so I can run it forward. And I get what is expected, and I can run it. Let's just run it straight backwards. And we get the expected output. So we've turned a relation, a function into a relation without interpretive overhead. Like you can see the generated code over here. So that's great. Now, what else can we do? Well, we can take a more sophisticated program Just a few words about the implementation. So we'll look briefly at staged mini-Cameron and then staged evaluation. So for staged mini-Cameron, the main construct is this lift. And what we've done is we've augmented the state to also have this code compartment. And lift just returns the state as it is, except that it adds the X code into the compartment. And lift was used to define L equal, so lifted unification. And there's also a more sophisticated form called lift scope, which allows you to generate code, but within a certain scope. And we'll see an example of this shortly. Now let's take a look at the staged eval expose. So we take stage as a parameter because sometimes when we call closures, we need to unstage things. But the invariant that we want to hold is that the expression is known and the value is unknown or dynamic or reserved for the second stage. And there are some complications because we still want to have variables in the expression, but basically that's the invariant that will follow when reasoning about this code. And so we look at number, for example. If we're staging, then we lift the unification, otherwise we use the unification right now. And as another example, we can look at how if is implemented. And here there's a subtlety due to the fact that we want each branch of the if to generate independent code. And this is what we use lift scope for. So when we generate the then branch, we put all the resulting code into this variable C2. And when we generate the else branch, we put all the code into this variable C3. And then we generate a condi, we lift a condi where we have the then branch and the else branch. So here's an interesting example of a function turned relation, which is a proof checker turned theorem prover. And the proof checker was independently done by Matt Knight without considering the relational setting. And then once the relational interpreter existed, it was turned into a theorem prover. And that is part of the ICFP 2017 paper by Wilbert and others. So here we're going to turn it into, to turn the same proof checker into a theorem prover without the overhead of interpretation. And so how to read this? Well, first here we have some pattern matching against a proof. And a proof is represented by a list, conclusion, assumptions, rule name, subproofs. And the conclusion is a term. The assumptions are a list of terms. The rule name is for bookkeeping, one of the three rules: assumption, modus ponens, or conditional. And the subproofs is a list of 0 more proofs that are needed to go from the assumptions to the conclusion. So let's look at the code itself here. So if we have an assumption, that means that the conclusion has to be a member of the set of assumptions. If we use modus ponens, that means that we're deriving B from A imply B and A. And so this is what happens here in the body when we recursively check the implication and the A part. And then this is what we construct at the end. And then finally, for a conditional, we're going from B under the assumption A to A implies B. Okay, so let's load this in our staged interpreter. And now we can see what happens when we ask for the proof of this lemma, and we have to put it in a run, of course. And this should be proof. And we get the actual proof of this statement via application of modus ponens twice. And notice that it was very fast, instantaneous, like you can do it again. And we can handle much bigger proofs as well. Okay, so now let's look at another example from the ICFP 2017 paper. And the goal here is to generate a quine with quasi-quotes. So we need to augment our language with quasi-quotation, our core language. And the way to do this is to write on top of the relational interpreter another interpreter that understands quasi-quotes. So we have a little tower of interpreters here. And so quasi-quotes are handled here with this eval quasi function. And notice it doesn't handle nested quasi-quotes, but it works well for having quasi-quotes at the outer level. Another thing to notice is that we use higher order representations. So in the evaluate, we use the first order representation where lambdas were represented by closures and environments were represented by association lists. And here we use a high order representation where a lambda is represented by a lambda and an environment is represented by a function as well. And we start with a function that doesn't understand any bindings, and then we can make it understand bindings one by one through just equality and inside the body of the extension. Okay, so we have this quasi-quote interpreter inside the interpreter, and now we're using our staged interpreter for the first level. So that means we only have one level of overhead instead of two. So let's see if we can generate quines. So here is the query for quines. And let's try it. So it's not instantaneous, but it came back pretty quickly. And we can see that it found this, our typical quine here, which if you evaluate, evaluates to itself. So let's just replace the and we can see that we get the same thing back. Okay, so running backwards faster with stage relational interpreters, that's what we've seen today. And just to recap, so stage means multi-stage programming, and we can do it functionally. And here we, as something new, we do it relationally. And relational means is exemplified by the language mini-Canran. And it allows, by running an interpreter inside of a relational setting, we can turn functions into relations. And then running backwards, meaning no distinctions between inputs and outputs. So for example, we can generate quines from a relational interpreter. And faster without interpretive overhead, we get rid of that through turning interpreters into compilers. And as another recap, so we saw the language mini-Canran, relational programming. We saw Evalo, which is an interpreter for a functional language inside the relational language. We saw Pink, which has polymorphic staging and is used to collapse towers of interpreters. We saw Stage mini-Canran, which is adding lifting constructs to mini-Canran to enable staging. And we saw Staged Evalo, which turns Evalo into from an interpreter of a functional language to a compiler from functions into relations. And that's it. Thank you very much.